Okay, so our next proof is talking about a rhombus, and if we go back once again to the different types of quadrilaterals, we kind of have subsets. So underneath parallelograms, we had rhombus, we had rectangle, we had square, and those shapes were all parallelograms, but there was something even more special about them that made them even more unique. So a rhombus was different than just a plain old parallelogram because all of its sides are congruent or equal. And so if you see, I've been given that JKLM here is a rhombus, and you can see that I've noted that all of these sides are congruent, and that is the definition of a rhombus. So a rhombus is a parallelogram, which once again is a shape, a four-sided shape with opposite sides being parallel. So all these sides are parallel, and because it's a rhombus, that means that all these sides are going to be the same as well. So that makes it a little bit more special than the parallelogram. It kind of defines it a little bit more. Okay, and I want to prove that line segment JL is perpendicular. That means perpendicular. It's perpendicular to line segment MK. And so these are my diagonals. So I want to prove that these diagonals are perpendicular. Okay. And if you remember our last one, we were talking about diagonals of parallelograms. Now we're talking about diagonals of a rhombus. So let's see what makes a rhombus special in the diagonals of that. So our first statement is always the given statement. So I'll start with JKLM is a rhombus, and that has been given to me. Okay. Now, next I'm going to say that line segment JM is congruent to line segment JK. And we know that because that's the definition of a rhombus. So this is a line segment JM is congruent to line segment JK. That's the definition of a rhombus. So once again, it's important to know the definitions of things and what makes them special so we can use them in our proofs. Okay. Now, I can also say, and I already have it labeled, but I'll put it in red so that maybe a little bit doesn't do anything really. Okay. I can also say that line segment MN is congruent to line segment KN. So I can say that these two are congruent. And how do I know that? Well, flip this around. We just did a proof that proved that diagonals of parallelograms bisect one another. Bisect means cut in half, which means that the right side is equal to the left side. Okay, so that means that MN would be congruent to KN. Remember, a rhombus is a parallelogram, so I can use that proof on this statement here. So line segment MN is congruent to line segment KN because diagonals of parallelograms bisect one another. So coming in handy already. Okay, awesome. So I have a side and a side there. And now I can also say that line segment JN, easiest proof out there, is congruent to line segment JN. A line is equal to itself, pretty obvious, and that is reflexive. So I'll do 3 lines there. So I have congruent, congruent, and congruent. And so this tells me then that triangle JNM is congruent to triangle JNK by side, side, side. So once again, by breaking this down into triangles, it really opens up a lot more ways and statements that I can prove things. Okay, well, because of that, now I can say that angle JNM, so angle JNM, is congruent to angle J, and K. And once again, if I take this triangle, I cut it out, I lay it on top of this triangle, this side's congruent to that side's congruent to that side is congruent to that side. Those two angles would be in the exact same spot if I laid it on top of each other. So I can say that these two angles are congruent because of congruent parts of congruent triangles are congruent, or my CPCTC. Okay. Now, where do I go from there? Well, again, I'm trying to talk about these two lines are perpendicular. So let's say that, let's see, that angle, and I'm going to say the measure of angle. Remember, the measure of an angle talks about a number. I'm going to go ahead and throw that in there to make it a little bit easier on ourselves here in the future. So the measure of angle MNJ plus the measure of angle JNK, so those same angles we were just talking about. Those two angles, they are going to be supplementary, or when added together equal 180 degrees. And if we think about our parallel lines and transversals, right? These are parallel, right? And this makes a straight line. So when I cut that straight line in half, straight line's 180 degrees. So when I cut that, well, these two angles, whatever they are, have to add up to 180 degrees. And that is my linear pair. Okay. And I'm going to go ahead and throw a measure up here with my angles just to save us some time. Now, so I have the measure of angle J and M is congruent to the measure of angle J and K, and I have the measure of angle J and M plus the measure of angle J and K equals 180 degrees. So now I can use substitution to say that the measure of angle J in M plus the measure of angle J in M equals 180 degrees, and that's substitution. So I basically took this J and M, since it's equal to or congruent to J and K, I just plugged it right in. Well, by using some simple addition, I have two of these, right? I have the measure of angle J and M and the measure of angle J and M, so I have two measures of angle J and M. Those equal 180. This is just addition. And by dividing both sides by 2, I can say that the measure of angle J in M equals 90 degrees. And that is just simple algebra, solving for my angle. So if I look over here, I have angle J and M is actually a 90-degree angle. And if we think about what's special about perpendicular lines, I'll go ahead and write it down. Line segment JL is perpendicular to line segment MK. What is special about perpendicular lines? Well, perpendicular lines cross at a 90-degree angle. Okay, so since these two lines, they cross it in, and this angle right there is 90 degrees. So they cross at 90 degrees. They cross at perpendicularly. They're perpendicular. So I can prove this statement by the definition of perpendicular lines. So this was a longer proof. We had a lot of steps that we had to take to finally get there. But by figuring out that these angles, and I could have proven really for any of the angles, that angle is 90 degrees, proves they cross at a 90-degree angle, which is the definition of perpendicular lines. So this tells me that diagonals of rhombuses, or I don't know what plural of rhombuses, we'll go with rhombuses. Plural of rhombuses bisect perpendicularly, or are perpendicular bisectors of one another. Okay, so if you think about our parallelograms, okay, they bisect, but they could bisect at any angle. They just had to bisect. But here, the rhombus, we've been told, we know that a rhombus, the sides are the same length. Okay, so that defines a little bit more, but it also helps us out by knowing that the diagonals bisect at perpendicular or 90-degree angles. Okay, so that's a little bit more of something special or characteristic of a rhombus. Okay, and remember we can also use this reversely. So if you have two lines, okay, two diagonals that cross at 90-degree angles, okay, they bisect at 90-degree angles, then you would have a rhombus.